So Mikhail contacted me some time ago with his interesting scientific discovery, which was unusual for me. Now I'm happy to give him the time to present this seminar based on his research work.
Thanks so much. Yeah, thank you for the opportunity. My name is Mikhail Trofimov. This year I've started doing physics, and I believe that I've discovered something, and I'm happy to share that with you today. Let's start with Newton. He first discovered this equation of gravity. Obviously, you all know that equation. You have learned it at school. But then Einstein presented his theory of special relativity, and this theory is based on two postulates: that the speed of light is a constant, and the physical laws are the same in all reference frames. From these two very basic postulates, he discovered the time dilation effect, the length contraction effect, and also the mass-energy equivalence principle. And then he applied the equivalence principle to the special relativity, and based on that equivalence principle, we've discovered the general relativity, that curvature of space-time is related to energy. And from this remarkable theory, we've discovered many insights like light bending, expansion of the universe, gravitational waves, and black holes. I think that right now this theory is incomplete. And first I would like to show and to share why do I think that general relativity is incomplete. First reason is the conservation of energy. In general relativity, energy at a global scale is not conserved. It's conserved only locally. The second reason is dark matter. So basically, general relativity cannot explain our observations of different gravitational effects like spinning of galaxies and gravitational lensing and many other observations. So because of that, we've had to add additional gravitational effect, and it's called dark matter. But at the same time, we do have a very successful empirical formula called MOND, modified Newtonian dynamics. It works very well, but nobody knows why. Third reason is dark energy. Some force that pushing galaxies away with acceleration, again, unexplained observation from general relativity. Combining all of that, we have only 5% of visible matter, and 95% of all the energy of the universe is unexplained. So basically, it's combination of dark matter and dark energy. Fourth reason is the inflation. To explain the homogeneity of the universe, we've had to add this an exponential expansion when everything started. To add this, we've had to add the inflaton field. Again, some unexplained energy that we've had to add to this theory. Fifth reason is singularities. General relativity predicts singularities, especially for black holes. We do have to basically, and physical substances within black hole. It's a point of infinite energy density and zero size called singularity, and also the event horizon, the place where time stops completely. Sixth reason is the Hubble tension. When we're comparing measurements of expansion of the universe made by the cosmic microwave background and by local measurements, it differs by about 10%. Also recently, James Webb Telescope has discovered early galaxies that again cannot be explained by current lambda CDM model. Recently we've discovered that dark energy is not a constant. It's evolving. The amount of acceleration is decreasing right now. And the ninth reason, general relativity is incompatible with quantum mechanics. It is one of the biggest problem in physics right now. So because of these 9 reasons, I believe that general relativity is incomplete, and the goal of my theory is to explain all of that problems and provide solutions. This is the plan of my seminar. Next, we will define the space-time field based on the time-energy equivalence principle. Then we will define the entropy equilibrium. After that, we will have the field equations with a natural explanation of MOND. Next, we will see how it explains dark energy and inflation. Then I'll show you cosmological tests I've performed. The last one we will conclude and discuss predictions. The time-energy equivalence. That Jacobson in 1995 discovered that general relativity, so an Einstein equation, could be derived from the closest relation, so basically from the first law of thermodynamics. He speculated that Einstein's equations are not describing space-time, but they're describing the wave propagation in the space-time. So this equation is not describing the medium of the wave propagation. So let's define this space-time medium. And to define that, let's go back to the equivalence principle again. What does it mean? It means basically that we have energy is described by momentum and mass, and we do have mass-energy equivalence principle here, and this energy curves space-time by the Einstein equation. What then happens? With bigger amount of energy, we do have time dilation effect and space attraction effect. So we do have this kind of connection. With more energy, we have stronger gravity, we do have smaller space and a slower time. What I'm proposing is just to combine this and say that energy and time are equivalent to each other. So with more energy, we're experiencing slower relative time. Basically, my principle says that any form of energy density is equivalent to a localized slowing of the rate of time. Then, what do we know about the energy from quantum mechanics? In quantum mechanics, energy is frequency. We may say that with higher frequency, we're experiencing slower time. And I'm connecting the quantum frequency with the time dilation effect here. And let's define the time flow field. This is a scalar field that consists only 2 properties, the frequency and amplitude. Frequency is related to time and amplitude is related to space. Also, to satisfy the main postulate of special relativity, we're defining the relation between the frequency and amplitude, and it is a speed of light. Then, let's define what is matter. Matter in that field are solitons. I've made this simulation by combining my ideas of chaos and order. So this is one of the examples how solitons could form from pure chaos, basically. That's what I think is matter. So matter is basically the coherent resonance of this field, the ordered part of this field. And we can divide the total energy of the universe by two parts. So the matter energy is basically all the radiation, light, and particles we're observing, and also the vacuum energy, everything else from of this field. And also let's define the vacuum frequency, the base amount of frequency, the lowest possible frequency in this field. So from that we have a space-time fluid where energy is defined by its frequency. Let's go to the entropy equilibrium next. This is the first law of thermodynamics, and it's based on the conservation of energy principle. In a closed system, work and heat should be equal. And based on that principle, I'm proposing that in the universe there are two main forces. One force is the force of chaos. It's basically the heat. And the other force is the force of order. So it's basically gravity. And when here you can see how from the cloud of gas a galaxy is forming. And what's happening here? So basically we do have two kind of entropic forces right now. The one force is structuring force, the force that creates more structure, like from the gas when we're forming galaxies, stars, biological life, and all other structured matter. Another type of energy we can see here is the heat that's producing because of that ordering force. And I'm proposing thus that these two forces should be equal. Because of that, we can define the chaos entropy and order entropy. So order entropy is basically the negative entropy, the entropy that creates more structure, less amount of chaos. And these two types of entropy should be equal. The total amount of entropy is basically zero, because the chaos entropy and order entropy should be equal to each other. Based on that, I'm proposing my second principle, that total entropy of the universe is dynamically balanced by structuring and dissipation, and sum of chaos and order entropy remains zero. Next, let's talk about the field equations and MOND. Again, let's go back to Ted Jacobson. He has discovered that Einstein equations could be derived from the closest relation. And what it means that if we take my entropy equilibrium principle and apply this to the closest relation, we're getting this effective entropy. And this entropic competition is defined by the critical temperature and by the function how these two entropic forces are impacts each other. So let's define the temperature first. We do have a Gibbons-Hawking temperature that describes cosmic horizon, and we do have Unruh effect that describes the thermal bath experiencing during the acceleration. So because of that, we are defining that Gibbons-Hawking temperature and Unruh temperature are related by the 2 pi. Let's define the non-linear function of this equilibrium. Basically, we do have the chaotic force and ordering force. We can express it by tangential state or radial state. So we do have these two kind of forces. And we can make a simple model where we have the fraction of bits of the disordered state and the ordered state. And from that, we're getting the interpolating function that looks exactly like MOND interpolating function. This function is just relation of order and to the total amount of energy. Then we take the Eric Verlinde latest discovery that Newton's law also could be derived from the thermodynamics, and when we are applying this entropy equilibrium function to the Eric's Verlinde discovery, we're getting the MOND formula. So basically, the MOND formula is a direct consequence of this entropy equilibrium principle. Then we're having the Jacobson's discovery of derivation of Einstein equation from the thermodynamics. Again, we're applying this entropy equilibrium principle, and we're having this field equation. This field equation, basically, it's just a small modification of Einstein's equation, and it could be also presented in a different form. So we do have matter entropy and matter energy and vacuum energy. So basically the ordered energy and chaotic energy. Basically this equation is equivalent to this equation, and this one is the total energy of the universe. From that equation, we can naturally explain the MOND formula, the Tully-Fisher relation, and radial acceleration relation, the most successful empirical laws that we discovered about the galaxy rotation. Next, dark energy and inflation. First, let's define the vacuum frequency. I am modeling this vacuum frequency from the tunneling rate, and basically we're having this Planck time, so 1 divided by Planck time is Planck frequency. Then we have the tunneling probability, and we're modeling it as a probability density to produce electron-positron pair, and fine structure constant is the efficiency of that effect. And from that, we do have two very basic and simple formulas. What is the MOND constant? And this is the vacuum rate of expansion. So this is the Hubble constant, but only within the vacuum. We can make a simple calculations, and here we have the very close to the observed MOND acceleration, and also we do have the vacuum driven expansion, so it is obviously higher than the observed and calculated expansion made from the cosmic microwave background. Then let's define the Friedmann equation. Applying the metric, we're having this Friedmann equation, and basically this equation could be transformed to this kind of equation. So this is a total energy density. This is matter density divided by this new function, derived from the entropy equilibrium principle. So, and we're defining that this is ordered energy density. So basically all light and matter we do have in the universe, and this is the chaotic energy and density. So basically the vacuum energy. Then let's apply the holographic principle to the total energy of the universe. So we do have this, the total energy of the universe is the circumference, and the ordered energy could be defined as diameter. Because of that holographic partition, we can define that the ordered energy is 1 divided by pi, and the chaotic energy respectively is all the rest. This is very close to our recent observation. So Planck energy fraction is almost the same as I've described by this holographic partition. Then we have this amount of chaotic energy, and then we are applying it to our discovered vacuum Hubble constant, and this is the observed vacuum constant modulated by the vacuum energy, because expansion of the universe is driven only by vacuum, not by the total energy of the universe. Then let's define what is chaos density and order density. The chaotic density should be related to the unused capacity of the horizon, and the order density is made from two parts. It's matter, it scales by the volume, and radiation scales by volume plus wavelength. So because of that, we're defining the chaos density and order density. So this is just all the matter, and this is all the radiation. And chaos density is just everything else. So all the rest energy of the universe. From that, we're having this equation where 1 divided by pi, this is the total order energy, and this part is the chaotic energy. It could be simplified to this form because this is just 1 divided by pi, so we can have this simplified form of the equation. Next, let's talk about the evolution of the universe. This equation at the 0 point, it predicts exponential expansion, so basically the de Sitter expansion. But this is just a simplification because of vacuum fluctuations, we don't have this exact 0. So chaos order and density and it's not exactly 0. So that's the reason why we're having this exponential equation driven by the radiation. So basically this equation then predicts this exponential expansion driven by the radiation, but it is a quasi-de Sitter expansion because we're experiencing this particle creation process. And the next part is the structure formation. So when the matter density is the highest, so this equation predicts matter-driven epoch of the universe. And then we have the current epoch. This equation basically predicts the evolving dark energy. So this part of the equation is not a constant. So that's why the dark energy is decreasing. And this is just a check of the consistency of the equation. So in current epoch, when A is 1, we do have this current Hubble constant. Then what's happening next? Next, when we do have the scale factor at about pi, we are experiencing the big stop. So basically, based on that equation, our universe should stop expanding when it will be about 3.2 times bigger than now. And after that, this equation predicts the space contraction of the universe. After that, our universe will be contracting back to the initial state, back to the inflation. Let's talk about the tests of this equation. and how it works. To test this theory, we can have this cosmological framework we've just developed, but for the local observations, we can use no free parameters model. So basically, we just derived the Hubble constant from the vacuum frequency, and we've discovered the matter and vacuum partition of the universe. And because the radiation is negligible at current epoch, we can have this simple equation. We're comparing this model with classic lambda CDM. Here we have 4 free parameters for lambda CDM, the Hubble constant, matter fraction, and also we do have 2 free parameters, the calibration for the supernova and the sound horizon. Also, we are measuring the goodness of fit using chi-square, and then we're calculating the big score to compare these 2 models to each other. And we do have 2 free parameters for Timeflow Gravity model and 4 free parameters for the lambda CD. To perform the tests, I am using 3 datasets: the Pantheon class dataset based on the observations of supernova, the Cosmic Chronometers, the direct measurements of the expansion rate, and also the recent results of dark energy observations made in this year, in 2025, to compare it with baryonic acoustic oscillations. Timeflow Gravity predicts lower deceleration parameter. This equation predicts very similar age of the universe to the lambda CDM, a little bit lower but still consistent, but more gentle acceleration. This equation predicts evolving dark energy, and it is quite consistent with recent observations. So this is how it performs with the Pantheon class dataset, and it has a bit better chi-square results than the standard model. These charts are for baryonic acoustic oscillations, again a bit better chi-square than the lambda CDM. The Cosmic Chronometers, here lambda CDM outperforms Timeflow Gravity, and also I've calculated probability distribution. So basically this is the Hubble tension in chart. So here we can see the probability distribution for the lambda CDM model, and this is the probability distribution of the Timeflow Gravity. And basically Timeflow Gravity eliminates the Hubble tension, and it predicts exact sound horizon consistent with the observations. This is the results. Also, I've calculated acoustic angular scale using the Timeflow Gravity equation, and again it's outperforms lambda CDM. And this is the results of the comparison. So Timeflow Gravity has 4 points better chi-square than lambda CDM with 2 free parameters. And if we calculate big score and compare to these 2 models, we can see that Timeflow Gravity outperforms lambda CDM by 18.5 points. And now let's talk about the predictions. First of all, this theory predicts repulsive voids, so we should observe much higher repulsion within voids than lambda CDM and general relativity predicts, and we can observe it right now. The next prediction is the environmental Hubble constant. So basically the Hubble constant could correlate inversely with the large-scale matter density. So basically we should observe higher amount of Hubble constant within voids than within high-density environments. And now let's conclude. Special relativity is based on two main postulates: that the speed of light is a constant and that physical laws are the same in all reference frames. I'm proposing a third postulate. I'm basing my theory that total energy of the universe is conserved. And from these three postulates, we can get the time-energy equivalence principle and the law of entropy equilibrium. And from this, we have to find what is time, what is space, what is energy, and what is gravity. And from this, we've got this modified Einstein's equation that explains most of the problems I've mentioned in this seminar. So it explains the MOND formula and inflation. It explains dark energy and most of recent observations, and also solves main theoretical problems of general relativity. I haven't covered singularities or quantum gravity today, but I believe that this theory could provide a path to resolve black hole singularities and finally combine quantum gravity, quantum mechanics with gravitational theory. I think that Timeflow gravity can explain how our universe evolves. Thank you. I'll be happy to answer to your questions.